Okay, what if I told you that every single computer you have ever used, from your phone to your laptop to the massive servers running the internet, has a fundamental hidden flaw? A quiet kind of error that can cause absolute catastrophe without ever triggering a single alarm. Well, today we're diving into a revolutionary patent that claims to have solved this very problem, a glitch that sits right at the core of all modern computing. So here's how we're going to break this down. First, we'll expose the glitch itself, a surprisingly simple error with massive consequences. Then, we'll get into something called the verification trap, which is why our current systems are completely blind to this. From there, we'll explore the wild idea at the heart of the solution, see how it creates a self-correcting memory, and finally, wrap our heads around what this new foundation of trust really means for the future of, well, everything. All right, to really understand what's at stake here, the patent lays out this perfect, kind of scary scenario. It shows just how easily our digital world can fall apart, even when the hardware itself is working perfectly fine. So picture this. You've got an AI, an autonomous trading agent. It's got the green light to make financial trades using the data from account A. But then, deep in the computer's memory, something silently shifts. A little invisible drift happens. Now the agent is still running perfectly, but it's pulling data from account B. It starts firing off trades for the wrong person with the wrong money based on a totally different strategy. And here's the kicker. The computer has no idea anything is wrong. No error messages, no alarms, nothing. It is functioning perfectly, just on the wrong reality. Right, so your first question is probably, hang on, why can't we just detect this? Seems like something we should have a check for. And you think so. But this is where we fall into a fundamental trap in how we verify data. A trap that's been around for over 50 years. See, here's the core of the problem. We are great at detecting data corruption. That's when the actual bits get messed up. A 1 flips to a 0, things like checksums can spot that in a heartbeat. But this problem is data displacement. The data itself is perfect. Not a single bit is out of place. It's just the completely wrong piece of data. So when our trading bot grabs the account balance for account B, the checksum looks at it and says, yep, looks good to me, because it can only verify that the data is intact, not that it's the right data in the first place. And this quote from the patent filing, it absolutely nails it. The machine isn't broken. It's not malfunctioning. It is following its instructions perfectly. It's just doing it with the wrong information. It's a state of confident, blissful error. This whole thing leads to a really deep kind of brain-twisting computational paradox. If you try to write software to check for this problem, well, that software checker can suffer from the exact same drift. So then you need another program to check the checker, and another one to check that one, and on you go into this useless, infinite loop. It really is like trying to see the back of your own head without a mirror. Any attempt to check your own state is fundamentally flawed from the get-go. So if software can't fix this, what can? Well, this is where things get really interesting. The patent proposes a completely new foundation for computing, one that sidesteps the whole paradox by just throwing out a 50-year-old rule. Here it is, the big idea. In every computer today, a piece of data's memory address is just an arbitrary location. It's the where. It tells you absolutely nothing about the what. This patent asks this simple but incredibly profound question. What if the physical address wasn't just a location, but was fundamentally tied to the data's identity? What if where the data is tells you exactly what it is? And this leads us to the core principle of the whole thing, positional equivalence, or S equals P equals H for short. It just means the data's logical structure determines its physical location in the hardware. The address is no longer random. It's precisely calculated based on what the data represents and where it belongs. In this system, location and meaning become the exact same thing. Okay, I know that still sounds pretty abstract. So how does this new way of organizing memory actually work in the real world? What does it look like in practice? Think of it like this. Today's computer memory is basically a chaotic library where the librarians are constantly moving books around. The card catalog might say a book is in one spot, but when you get there, someone's put a totally different book in its place. In this new S equals P equals H system, the library is perfectly rigidly ordered. A book's call number is its physical location on the shelf. You literally can't put a book in the wrong place because its identity is its location. Any displacement is immediately physically obvious. So once you have this perfectly ordered library, you can build something that honestly sounds like science fiction. A memory that knows when it's wrong and then fixes itself automatically at the speed of hardware. Let's look at the elegant little mechanism that makes this whole thing possible.
They call it the geometric drift control loop. Here's how it works. First, the memory is laid out in these identity neighborhoods. Think of them as dedicated zones for specific, related data. Now, if a program tries to access data that has drifted outside of its proper zone, it trips a digital tripwire. That tripwire is actually a physical cache miss event. Normally, a cache miss just means a slight delay. But here, that signal is repurposed. It alerts a dedicated hardware circuit not just that the data is missing, but that it's in the wrong place, and that circuit can instantly fix its position.
And get this entire loop, the drift, the detection, and the correction, happens in about 5 nanoseconds. That's 5 billionths of a second. It's an almost incomprehensibly fast physical response. And just to put that number in perspective, a typical software-based check takes anywhere from microseconds to milliseconds. That's an eternity in computing terms. This S equals P equals H hardware correction is happening right down at the physical level, and it is orders of magnitude. We're talking potentially millions of times faster than any software could ever hope to be. It's not even in the same league. This incredible speed, this physical grounding, it all leads us to what is, for my money, the intellectual peak of this entire invention. It's a moment where two separate, fundamental actions of computing just completely collapse into a single event. You have to understand, in every computer ever built, up until now, reading data and verifying data are two totally distinct steps. First, the processor grabs some bits from memory. Then, as a completely separate action, it might run a check to see if those are the right bits. It's always read, then verify. But in this new system, a regular old hardware event gets a superpower. A cache hit normally just means the computer found the data it was looking for really, really fast. It's a performance thing. Here, because a data's location is its identity, a cache hit doesn't just mean the data was fast. It also inherently proves the data is correct. Because if it was in the right place to be a hit, it has to be the right data. And this, right here, is the ultimate payoff. They call it the retrieval-verification collapse. The physical act of reaching for the data becomes the exact same single hardware event as verifying that data. You don't read and then check. The read is the check. Verification becomes a free, instantaneous, physical byproduct of just using your computer. It's honestly mind-blowing. So, what's the big takeaway from all this? Why does anchoring our digital world to physical reality so fundamentally change our relationship with technology? Let's talk about the future this could unlock. Well, in a world that's becoming more and more reliant on AI and autonomous systems, trust is everything. This architecture provides a physical anchor for digital trust. It gives us a way to know, down at the silicon level, that an AI is working with the right information. It gives us real confidence that an autonomous car or a trading bot is still the same trusted entity it was a millisecond ago. The machine becomes physically incapable of lying about where its data is, and therefore, what it's actually doing. And this leaves us with one final, pretty provocative thought. For decades, we've built these incredible systems on a foundation of computational trust, and we're learning just how fragile that can be. This technology points to a future built on provable physical truth. So the question we're left with is this: what becomes possible when our most powerful machines are incapable of lying about who they are and what they're thinking?